We can express the average rate of change of a function over an interval in multiple ways. So using the rise over run in this first case, the rise would be f of a plus h minus f of a over the run, which is a plus h minus a. And in this second case, so these are the slopes of the secant line. And from the average rate of change, we can obtain an instantaneous rate of change at x equals a by taking the limit as h approaches 0. So as h gets smaller and smaller, we get a better approximation to the slope of the tangent to the curve at a. And basically the tangent touches the curve only once at a. And similarly for this second case, if we take the limit as x approaches a, then in a similar way we get a better approximation to the slope of the tangent to the curve at a. And that's provided that these limits exist. So these two are equivalent forms of the derivative evaluated at a, which we denote f dash of a. Let's do a more formal definition of the derivative. So what we do first is take the average rate of change between 2 points, or the slope of the secant line. So that will be the rise on the run, which is x plus h minus x. And then if we take the limit as h approaches 0, we obtain the slope of the tangent to the curve at x. So for example, as h gets smaller and smaller, we get another secant, and that gives a better approximation to the slope of the tangent to the curve at x. And this tangent touches the curve only at x. Okay, so this slope of the tangent line is the derivative, which is denoted f dash of x, provided that this limit exists. So other notations you may see for the derivative is dy dx, y dash of x, and so on, which is the instantaneous rate of change at x. Let's evaluate this derivative using the definition. So we have the limit as h approaches 0, and our function is root x. So that will be root x plus h minus root x over h. And we multiply this by the conjugate in the numerator and denominator. So that will be root x plus h by root x plus h, then minus root x by root x over h multiplied by the square root of x plus h plus root x. And now we can see that x is going to cancel and h is going to cancel, so we get 1 in the numerator, and this limit thereby evaluates to 1 over 2 root x when h approaches 0. Let's prove this derivative using the definition. So we take the limit as h approaches 0 of 2 to the x plus h, which is the same thing as 2 to the x by 2 to the h, then minus 2 to the x, so we can factor out 2 to the x on h. And now we let u equal 2 to the h minus 1. So if we take the natural log of u plus 1, and that's equal to h by the natural log of 2, and then just divide by the natural log of 2. And now we can substitute back into this derivative. So if we take 2 to the x outside by the limit, and when h goes to 0, u goes to 0, and in the numerator we have u over h in the denominator. So that would be the natural log of u plus 1, and then we multiply by the natural log of 2. And therefore this is a limit of 0 on 0. So by L'Hopital's rule, you'll be able to get this is equal to 1, and that proves our derivative. We can represent the derivative in a number of ways. So here we represent it graphically as the slope of the tangent line to the parabolic curve at x equals 2. So if we choose 2 points, we can obtain the rise over the run. Now we can also approximate the derivative numerically. So here we have the function evaluated for several x values. So again we can approximate the derivative at x equals 2 using the rise over the run. So that would be 9 minus 4 on 3 minus 2. So in this case we've chosen x equals 2 and x equals 3. So it's going to give a steeper slope. Now we can also represent the derivative analytically. So here you could have used the definition of the derivative. So we take the limit as h approaches 0, and then using our function, and if you evaluate this limit, you'll obtain this result. And we can also represent the derivative verbally as the instantaneous rate of change of a function y with respect to the independent variable x at a particular point. Let's estimate the derivative graphically and using the information from this table. So we suppose that we want the derivative at x equals 3. So we draw a tangent line that only touches this point on the curve. as best as we can. So using the point at x equals 4 and the point at x equals 3, we have the rise, which is 15 minus 9, on the run, which is 4 minus 3. And similarly, if we want f dash of 3 using the table, well, what we need to do is choose the x values that are closest to 3. So the rise would be 16 minus 4 on the run, which is 4 minus 2. And that gives us the same result. And this happens to be the exact value of the derivative of this function at x equals 3. And sometimes you can get the exact value for simple curves like this. Let's use technology to estimate the derivative of a function at a point. So we did this previously by drawing the tangent line manually. So let's first plot our curve. So that would be x squared. And now to approximate the derivative, we can use second function, calculate, and choose option 6. And now we can enter an x value of 3, because we want the derivative at x equals 3. And that gives us dy dx is equal to 6, which is the same result that we've obtained using the graphical method here. A function is differentiable at x equals a if it's continuous and smooth at x equals a. And by smooth, we mean that this limit exists. So this function here is continuous, and as x approaches a from both sides, so we can draw the secant from both sides, so you can see that this limit is going to be the same from both sides at x equals a. Now for this function here, it's continuous, but it's not smooth, because as you can imagine, as x approaches a from the left, and as x approaches a from the right, you're going to have two different slopes. So in this case, the slope is infinite. So for these other two examples, from the right, we can see that this limit is going to approach a finite value. And from the left, if we draw a secant line, so therefore the derivative does not exist, because as x approaches a from both sides, this limit is not the same. And similarly here, the function is discontinuous, so the derivative does not exist. Is this function differentiable? So first we check for continuity. So f of minus 1 exists, and the limit as x approaches minus 1 from the left and the right is the same. So because these are equal, the function is continuous. And now we need to check if the function is smooth. So we take the limit as x approaches minus 1 from both sides of f of x minus f of minus 1 over x minus negative 1. So as x approaches minus 1 from the left, then we take this as f of x. And f of minus 1 is 3. And as x approaches minus 1 from the right, we take this as f of x, which simplifies as follows. So you can clearly see that these are two different limits, and without doing a factorization and evaluating them, and therefore the function is not differentiable. For functions with the independent variable x raised to a constant, the derivative evaluates to n multiplied by x raised to a reduced power by 1. And let's show that using the definition of the derivative. So we have x plus h to the n minus x to the n on h. And using a binomial expansion of the left-hand term, we obtain the following result. So x to the n cancels with an x to the n, and simplifying the following terms, we obtain the following result. And as we can see, as h goes to 0, this term and this term disappears, and we're only left with this term, which is the result of the derivative of x to the n. Similar to limits, we have derivative rules that can simplify the differentiation of functions. So here we have the derivative of a constant, which is always 0. So for example here, f of x equals 2 by x to the 0. And then using the power rule, what you do is put down the power and then reduce it by 1. So this will give 0. And similarly, we have sum, difference, and constant multiple rules that can be used to find the derivatives of polynomial functions. So for example, if we have the derivatives of the function x and a function g as d1 and d2, then the derivative of the sum of those functions is equal to the sum of the derivatives. And you can see the accompanying examples on the right here. And similarly for the difference rule, the derivative of the difference of two functions is equal to the difference in their derivatives. And the derivative of a constant multiplied by a function is equal to a constant multiplied by the derivative of the function. Let's evaluate the derivative of this function. So it may help to write it as follows. And now we can apply our derivative rules to evaluate the derivative of each term. So what we have is a constant, and apply the power rule to x squared, and then plus another constant root 3, and using the power rule we put down the half, and reduce the power by 1. And for the third term, we put down the power of minus 1, and reduce it by 1. And now we can simplify these as follows. Let's prove these elementary derivatives, and then remember them and apply them. So the left-hand side can be written as follows using the definition of the derivative. And using the addition trig identity, we can write the first term as follows. And now we can do a bit of factorization and apply the limit rules. Then we can split these up in two and evaluate them individually using the limit rules. So recall that this limit here evaluates to 0 as we've proven previously, and this limit here evaluates to 1. So therefore the derivative of cosine x is minus sine x. Let's prove the derivative of sine x, and there's another elementary derivative that we'll remember. So using the definition of the derivative, and now using the addition trig identity, we can simplify the first term as follows. And now we can do some factorization to split these limits into two. And we've shown previously that this limit evaluates to 0, and this one here evaluates to 1 as h approaches 0. So we basically split these into two limits using the limit rules. And therefore the derivative of sine x is cosine x. Let's use the definition to prove the derivative of e to the x. So we have the limit as h goes to 0 of e to the x plus h minus e to the x on h. And now we can do a bit of algebra to factor out e to the x. So we have e to the x by e to the h minus 1 on h. And now letting u equal e to the h minus 1. So we can add 1 to both sides and take the natural log. So that gives the natural log of u plus 1 is equal to h. And now we can take out e to the x outside the limit. And we have the limit as h approaches 0. So by this expression, when h goes to 0, u goes to 0. And then we have u in the numerator over h, which is the natural log of u plus 1. And we can see that this is the limit of 0 on 0. So we can use L'Hopital's rule to differentiate the numerator and denominator. And taking the limit, you can verify that this is equal to 1. Let's prove the derivative of the natural log of x using the definition. So we take the limit as h goes to 0 of the natural log of x plus h minus the natural log of x over h. And using the rules for logarithms, we take the limit as h goes to 0 of the natural log of x plus h on x. So that would be 1 plus h on x on h. So if we let u equal h on x, well that implies that 1 on h is equal to 1 on x by u. So when h goes to 0, u goes to 0, and we can substitute for 1 on h, so take 1 on x outside the limit, and keep 1 on u inside the limit. And in the numerator we have the natural log of 1 plus u. And this is a limit of 0 on 0, so by L'Hopital's rule, this here evaluates to 1, and that proves our derivative. The product rule is effective for a function which is a product of two functions. So using the definition of the derivative, and now we can add and subtract a term in the middle, so we don't alter this definition. And now we can group the terms together and break this up into several limits. And then using the product rule for limits, the limit of u of x plus h evaluates to u, and the limit of this term over here is v dash of x. And similarly for this second limit, the limit of v of x as h approaches 0 is simply v of x, and the limit of this term here as h approaches 0 is u dash of x. Let's differentiate the following function. So f dash of x of the first term can be obtained using the power rule, so that would be 4 by 3 is 12, and reduce the power. And the second term is a product of two functions, so we can use the product rule. So designating this function u and this function v, well we keep u constant and differentiate the second term, and then we differentiate u and keep the second term constant. Let's differentiate f of x, which is the product of a function u and a function v. So using the product rule, we can evaluate the derivative. So we first keep u constant, and then differentiate v. So x to the 1/2, using the power rule, becomes 1/2 x to the minus a half. And then this here is x to minus 1/3. So that will be minus 1/3 x to the power of minus a third minus 1, which is minus 4/3. And then we differentiate u using the power rule and keep v constant. And then doing a bit of simplification, we obtain the following result. We can also apply the product rule to a function that's a product of three functions u, v and w. So to evaluate the derivative f dash of x, we can keep u constant and v constant and differentiate w. And then we can keep u constant and w constant and differentiate v. So note that the derivative of cosine x evaluates to minus sine x. And then we can differentiate u and keep v and w constant. Then doing a bit of simplification, we can factor out 3e to the x. And you can also simplify this further using trig identities if you like. The quotient rule can be used to find the derivative of the quotient of differentiable functions. So this rule can be proven using the product rule and chain rule, which we'll learn later. But for now we can remember it using a simple mnemonic. So the derivative of this function is low d high. So the low function multiplied by the derivative of the upper function minus high d low over the lower function squared. And we'll apply this using several examples. Let's differentiate this function, which is a quotient of two functions. So the derivative we can obtain using the mnemonic low d high. So we keep the lower function constant and differentiate the upper function. And then minus high d low. So we keep the top function constant and differentiate the bottom function. And that's divided by low squared. And we can simplify this a bit by factorizing the exponential term. Let's evaluate the derivative of f of x. So f of x is g of x on h of x. And furthermore, g of x is the product of two functions, and then we divide by h of x. So what we do is first apply the quotient rule. So that would be root x kept constant, then multiply by the derivative of the function in the numerator. So we use the product rule to evaluate this. So we have cosine x by the natural log of x plus sine x by the derivative of the natural log of x. And then we subtract, keeping the function in the numerator constant, and multiply by the derivative of the function in the denominator. So that will be 1 over 2 root x. And all of this is divided by root x squared. And then doing some algebra, you'll be able to simplify this further. We can rearrange trig functions using trig identities and then apply the derivative rules. So tan x can be written as sine over cosine x, and that allows us to use the quotient rule to evaluate the derivative. So we have low d high, which is cosine x, and then minus the high function by the derivative of the lower function, which is minus sine x. And that's divided by the square of the lower function. So using the trig identity, we get 1 in the numerator, and that's equal to sec squared x. To find the derivative of the cotangent of x, we can use trig identities to write it as follows. So cosine x on sine x, and now we can use the quotient rule to evaluate the derivative. So we have low d high, which is minus sine x, minus high d low, which is cosine x. And that's divided by the square of the lower function. So we can write this as minus sine squared x plus cosine squared x, which gives minus 1 in the numerator using the trig identity. And therefore the derivative of the cotangent of x is minus cosec x squared. Let's find the derivative of sec x, which can be written as 1 over cosine x using the trig identity. And now we can use the quotient rule to evaluate the derivative. So we have low d high minus high d low. And that's divided by low squared. So that gives sine x over cosine squared x, which is also equal to 1 over cosine x by sine x on cos x. And therefore, using our trig identities, this can be written as sec x by tan x. And this is another derivative we can remember. Let's differentiate cosec x. So we can write this as 1 over sine x using our trig identities. And now we can differentiate it using the quotient rule. So we have low d high minus high d low. And that's divided by low squared. So this becomes minus cosine x on sine x squared. And therefore, we can write this as 1 over sine x by cosine x on sine x. And using our trig identities, this can be written as minus cosec x by the cotangent of x. And this is another derivative we can remember. Let's find the derivative of tan x by cotangent of x. Well, we can use the product rule, or use trig identities first to simplify the function. So tan x is sine x on cos x, and the cotangent of x is the cosine of x on sine x. And therefore, this gives 1, and the derivative of a constant is 0. So you've got to picture this as 1 by x to the 0, and using the power rule, the derivative of this evaluates to 0. Let's evaluate the derivative of this product of two functions. Now we could rewrite this as e to the x on sine x and use the quotient rule, or simply remember the derivative of cosec x and use the product rule. So we keep e to the x constant, and the derivative of cosec x is minus cosec x by the cotangent of x, as we've seen previously. And then we take the derivative of u, which is e to the x, and keep the second function constant. And now we can factor out e to the x by cosec x, and for the second term we have 1, and the first term is minus cotangent of x. Let's differentiate the product of two functions. So to do that, we'll apply the product rule. So keeping the first function in the brackets constant, and differentiating the second function, we get minus cosec squared x. And now we can differentiate the first function, so 3x to the minus 2 is minus 6x to the minus 3, or minus 6 on x cubed. And then we minus 10, and the 1 drops out, and we keep the second function constant. Let's differentiate the product of two functions. So we can either use trig identities and apply the quotient rule, or simply apply the product rule while remembering the derivatives of these functions which we've evaluated previously. So by the product rule, we keep tan x constant and differentiate sec x. So that evaluates as sec x tan x, and then we differentiate tan x, which evaluates as sec squared x, and keep the second function constant. So this becomes sec x cubed. Let's evaluate the derivative of the product of three functions. Now we can use either trig identities and the quotient rule, because cosec x is 1 on sine x, or we can apply the product rule. So let's just do the quotient rule in this problem. So we have low d high, so we use the product rule to evaluate the derivative of the function in the numerator. So keeping e to the x constant and differentiating the natural log of x, and then differentiating e to the x and keeping the natural log of x constant. And we subtract high, which is the upper function kept constant, and multiply this by d low, which is cosine x. And that's divided by the lower function squared. And I'll just leave it for you to simplify this further.